In this video, I will present mathematical models that are associated with rotational kinematics and energy. So to start out, we want to be able to relate tangential quantities to angular quantities. We already started to do that with the concepts. We've seen this already. So the arc length that we're talking about, so an arc length from one spot to another, is the radius, so that would be the distance from here to there, multiplied by the angle. So the angle would be from here around to there. So arc length is related to theta. Tangential velocity. Tangential velocity is the same radius r multiplied by the angular velocity. Similarly, the tangential acceleration is related to the angular acceleration. The same pattern here. So this is like a distance, a velocity, an acceleration. This is also like a distance, but it's an angular distance, angular position, angular velocity, angular acceleration. All right. Something to note, this is not the same as centripetal acceleration. Centripetal acceleration, remember, is pointed in toward the center. Angular acceleration is different. Angular acceleration is around, okay? So it's around the center. The angular can be this way. The centripetal is toward the center. All right. We've already had centripetal acceleration is v squared over r, right? Now we know that this v is actually vt. It's the tangential velocity because it's in the direction that goes around the radius. So vt squared over r, and actually if you look at vt, that's r omega. So this is the same as r omega squared over r, and r omega squared over r is r omega squared. Okay. So if you have angular velocity, you can go straight to centripetal acceleration. You don't need to actually calculate what this v was. The next thing is the period. So period means, for example, how long does it take for this piece of blue tape to go all the way around? So if I start it moving, it's the time it takes to come back to the same place, one time. That is a period. The time for one complete revolution or one complete rotation. Those two words can be used interchangeably, rotation and revolution. So a period is 2 pi divided by the angular velocity. On this side we have moment of inertia. I mentioned on the last page that moment of inertia is I. So you'll see there are a lot of different I's here. I for a hoop, I for a hollow sphere, I for a solid sphere, I for a rod held about the center position, I for a rod held at the end, I for a disk. The moment of inertia of an object depends on its mass, in all cases. It also depends on its size, either a radius or a length, but it also depends on the way the mass is distributed. So the shape of the object changes the moment of inertia of the object. This is a lot of equations on this page. Everything on this side you've already seen. We've done all of these equations before. This is just to remind you, right? So these are kinematics equations and kinetic energy, linear. Now let's look at these. So the average angular velocity is the change in the angle over change in time, or the final angular velocity plus the initial angular velocity divided by 2. Notice that this looks exactly like this, except that linear velocity has been replaced with angular velocity, and linear displacement has been replaced with angular displacement. That's the only difference. Same thing here. This is acceleration. Linear acceleration gets replaced with angular acceleration. Linear velocity gets replaced with angular velocity. All of these equations, all of the ones here, are exactly the same as here, except you replaced all of the linear components with angular components. On the last one, we have kinetic energy related to mv squared. So it'd be really nice if we could relate kinetic energy again to something times angular velocity squared. So that's what this I does. This I replaces m.